Hey everyone, welcome back to Math 7195. This is unit number 2, video 1. Today we're going to be discussing the basics of probability, do a bit of counting, work on the probability axioms, and then we'll do a few examples. So I think we can just dive right in here to unit 2. We'll start out with an introduction to probability. There's some notation here. We sort of write probability notation like function notation, where we let P be probability, and then we say the probability of some event A happening, read it as P of A. You've probably done probability before. We're going to approach this sort of the classical way where we investigate, games of chance. This is basically how this originated in the first place. Later, we will then apply probability in maybe a more useful way when we're talking about decision making. But for this particular unit, we're mostly just going to be, we start out with just playing with games essentially. We'll talk about dice and cards and coin flips and such, because that's where this stuff initially originated from. So we'll sort of follow the footsteps of how it was developed. Classical probability is defined here, where the probability of some event A happening is just the number of ways that A can happen divided by the total number of things that can happen. I'll denote that by S over N. That's sort of the ideal where you can calculate the exact probability of something happening. What's the probability of drawing a red card from a deck of cards? You count how many cards there are, that's 52, and half of them are red, so 26. So 26 out of 52 is the probability of drawing a red card, and we get the exact probability. Other times, we can't necessarily count the total number of ways that something can occur. So we may have to rely on doing an experiment. And then we get the relative frequency approach to probability, or we get an estimate of probability based on repeating something over and over again and keeping track of how often we're successful versus how often we've done the experiment. So that's basically the formula given here in 1.1. The law of large numbers will sort of link these two together. It basically says the more times you repeat the experiment, the closer your relative frequency approach will get to the actual or classical probability. There's a little picture drawn here where I was flipping coins and looking at the probability of getting heads. Probability of getting a head when flipping a coin. I flip it one time and I got heads, so I would estimate the probability is 100%. Then I flipped it again and I got tails, and then I got heads and tails and heads and tails, and I just kept track of the total number of times I saw heads out of the total number of times I flipped the coin. And you'll see that at the beginning, it's very volatile, but after a while, the thing starts to stabilize and get, very close to the theoretical value of flipping a coin and getting a head, which is 1 out of 2 or 1/2. So we will use this law of large numbers as we go along, whenever we're doing some sort of estimates of probability. I did a little example here of rolling dice. I wanted to know what's the probability of getting a 3 when I roll a single die. So I rolled a die 10 times on my coffee table, and I observed that I saw in 10 rolls, I saw 2 3s. So I estimate that the probability of rolling a 3 is 20%. And if you want to annoy people in your family, I recommend repeating this experiment. It sounds something like this. Now imagine doing that 1,000 times. I actually did do that. And after 1,000 times, I saw 162 threes out of the 1,000 rolls, giving me a probability estimate of 0.162, which is pretty close to the actual probability, as we know there are 6 sides on a die and only one of them has a 3. So the probability of rolling a 3 is 0.167. So at least to 1 decimal place, almost a 2 there after 1,000 rolls. You can see we have a bit of error, but the more we do it, the closer it should get. Here's another problem, one that's maybe not as obvious. We want to get a flush when playing poker. So we're going to play basic 5-card stud poker, meaning you just get 5 cards. There's no community cards, there's no drawing, there's no any weirdness, no wild cards. We're just going to play with the standard deck, and we want to know what are the chances of getting a flush dealt to us in 5 cards. A flush means all the same suit. So here's one that are all clubs. I will make the assumption on tests and things that you know what a deck of cards is. I won't make an assumption that you necessarily know how to play poker. To solve this problem, I would need to count all the different ways that I can get 5 cards of the same suit. And then I would have to count all the different ways I could get 5 cards, and then look at their ratio. It's not an easy task. I can't just start listing them out. I think I'd start to grow old attempting to list them, and I'd probably miss some. So I know many of you love computer programming. We could write ourselves a little program where we could try to simulate this, where we say, how many hands do you want dealt? And then we generate 5 unique cards, and then we check, are these cards all the same suit? There's one other little glitch that you run into, that in poker there are flushes and there are royal flushes and there are straight flushes. So we don't want to count the royal flushes and straight flushes. So we'll have to eliminate those. Those are flushes that are completely in sequence. So like 3, 4, 5, 6, 7, 8, all of the same suit would be a straight flush. And a royal flush is when it includes 10, Jack, Queen, King, Ace. So we want to rule those out. So I'd have to, whenever I generate my 5 cards, I'd have to then sort them and check to make sure that that it isn't a royal flush or straight flush. Because if it is, I won't count that as just a boring, regular flush. We can, once by coming up with computer code for this, we can, basically deal millions of hands rather than, if I took a deck of cards and attempted to do this, I could, shuffle the deck, deal 5 cards, is it a flush? Shuffle the deck, deal 5 cards, is it a flush? And yeah, I could do that, but it would take me, a long time in order to deal, say, thousands or millions or billions of hands. But if I write a little computer program that will do this sort of randomly, we can get our results that way. So here's my rather crude interface. I asked to run my program was called flush, and on the command line I input how many flushes I want dealt. So in this case, I ran it with 100 million. I hit enter. It thought about it for maybe a minute, and then it would spit out the results. So it didn't take very long even to do 100 million hands checking to see if they were flushes. So in my 100 million hands, my results were, I had 998 million that weren't flushes at all, 197,344 that were flushes, And I kept track of the straight and royal flushes just for fun. If you total those up, they do add up to the total number of hands. So, it's sort of a way to error check myself. So in this case, my probability of a flush is estimated to be 998.01124. I might be off by where my comma goes there. I guess I did 99. Oh, sorry, those are non-flushes. I'll get this right here. My flushes were 197,344, and I did 100 million hands. So that decimal is given here. I know the actual probability of getting a flush. I can either calculate it or I can look it up somewhere, and I output that just for comparison. You'll see that the first 4 decimal places, maybe even 5 if we rounded it to 5 decimal places, we would match the actual and the approximate there would be the same to 5 decimal places after 100 million hands. So there's a lot of work to do that. So I calculated the straight flush and royal flush as well, and I determined the error by subtracting the actual from the estimate. I'm off by 10 to the minus 6 on my flushes, and then 10 to the minus 8s on my straight and royal flushes. You'll see that I was maybe, because I guess it's positive, I was a little lucky. I ended up seeing a few more flushes than I actually expected. But then it was balanced out because I saw a few less straight flushes than I expected. So that helped make, add some legitimacy to this. I did 100 million a few times, and the results were pretty stable. So I feel pretty good that, my program is working correctly, especially because I did know the answer to this problem. So I was able to compare. So this is sort of what's known as a Monte Carlo simulation, where you repeat something over and over again, counting how many successes you have versus how many times you did it. And in this case, we used random numbers to do so rather than rolling dice on our coffee table. It turns out that you can calculate this exactly. The total number of possible flushes is 5,108. And the total number of 5-card poker cards is about 2.6 million there. So 5,108 divided by 2.59 million ends up giving us the exact value. So some problems can be solved classically, and then we can compare them to our Monte Carlo version. And other problems are so complicated that we can't ever do the counting, and therefore we're stuck with doing some sort of simulation. Speaking of counting, it's not the easiest procedure to do, but there are only a few rules to learn, I guess. The fundamental counting rule, where you have a bunch of different events and you count the number of times each one can occur. If you multiply them all together, that's the total number of ways that the outcomes can happen. The classic example, most of us are aware of the 649 lottery. There are 49 balls in a box, and 6 numbers are drawn from it, and it is the lottery player's goal to try to pick or predict which 6 of the 49 will be drawn. I was curious as to how many different ways this can be done. Like how many ways can you pick 6 things out of a group of 49? I tried using this multiplication rule, but not to a lot of success. I was trying to understand this by saying, okay, suppose I pick the number 1, and after I pick the number 1, what's left? I can't pick the number 1 again in that lottery. Once you pick a number, it's removed. After I pick the number 1, I'm left with 2 through 49. If my next number is, say, a 4, then I'm left with 2, 3, and then 5 to 49. And I tried to, if I could count all of these, pathways through, I could figure out how many different permutations there were. But there are a lot. Even if we reduced the number of balls down to, like in a problem like this, a common approach is to go, okay, I can't handle a box with 49 balls in it. Maybe what would happen if I picked a box that had 5, and then try to come up with an method for solving it with 5. But even listing out 5 might take me quite a while. If I use the counting rule above, on my first pick from the box of balls, I have 49 choices. And then after that, I have 48, and then I have 47, and 46, and 45, and 44. And basically, whenever you hear yourself saying the word "and," you should be thinking multiply. So we multiply all those values together, and we end up with, what is that, 10 billion? 10 billion different permutations, which seems high. There are only, 35 million Canadians. I don't think that we'd ever win the lottery if there was only a 1 in 10 billion chance. So there's something not quite right here. And I think we can kind of see it even in this, crude drawing here. I could pick, I could go 1, then 2, 1, then 2, then 3, then 4, then 5, then 6. But I could also pick 1, then 2, then 4, then 3, then 5, then 6. These two things are the same. They're the same 6 numbers. So we're counting groups of 6 multiple times, like they're appearing more than one way. Each group of 6 occurs a bunch of times. I can't even list all the different ways that I could write a group of 6 numbers. And I'm only using 1, 2, 3, 4, 5, 6. Remember, we have 7, 8, 9, 10, all the way up to 49. So I see why this 10 billion has come up, because we've counted each group of 6 multiple times. So we need to figure out how many ways are there of arranging a group of 6 things. I did it here. On the next page, suppose we have the numbers 1 through 6. How many ways can you rearrange them? Well, you have 6 choices for the first one, then 5, then 4, then 3, then 2, and then 1. If we multiply all those together, there are 720 different ways of rearranging the numbers 1 through 6. In our example for the 649, we had 10 billion permutations, but we were counting each group of 6 720 times, so I'm going to divide it by 720 and get a more reasonable answer there of roughly 14 million. The probability of winning on the 649 then is you buy 1 ticket, you have 6 numbers out of 14 million. It's funny, every time I buy a ticket, I feel like this is the day, this is the one, I'm going to win, and I don't have to record any more of these videos. But I think most of us have no concept of what 1 in 14 million means. I looked up some stats on, I thought an interesting stat to compare it to might be, what are your chances of getting killed by lightning? So I found that in the US, just to approximate the numbers here, there are around 300 million Americans. It's a little bit more actually. But each year, around 300 people are killed by lightning in the United States. So your chances of getting killed by lightning are roughly 300 out of 300 million, or a 1 in a million chance. Yet your chances of winning the lottery are 1 in 14 million. So you should get killed by lightning about 14 times before you win on your lottery ticket. When I buy a lottery ticket, sorry, I'm just going to jump over here and do a little aside on lottery tickets. We just found that your chances of winning are 1 in 14 million. I have to drive to the 7-Eleven to get my lottery ticket, and I wanted to see what my chances were of dying in my car while trying to buy a ticket. So I found some highway statistics, and they say that there's about 1.7 deaths for every 100 million miles driven. The 7-Eleven is about 3 miles away from my house. So a round trip visit to the 7-Eleven is a 6-mile journey. So 6 miles times 1.7 fatalities per 100 million miles yields this result, which is 1 fatality in every 9.8 million trips. So my chances of dying while getting a lottery ticket are actually higher than my chances of winning. So when I leave the house to go and buy a lottery ticket, I really need to consider that, as that's rather startling that I'm more likely to die than I am to win. Of course, this is a bit biased. I'm driving, these are highway statistics, and I'm not really driving on fast highways on the way to the 7-Eleven. So this is maybe an exaggerated example. I'm probably not going to die, or I think my chances of winning might be a little bit higher than my chances of dying if I factor in that I'm driving at a slower speed than highway speed on my way to and from buying it. But still interesting, I guess. So don't go out and buy a lot of lottery tickets, or don't go out back and forth driving to get lottery tickets. Stay home and buy them online, I guess. So yeah, that's just to give us a little bit of a number sense. I have a hard time with probability in that it is hard to have a number sense, even for more familiar things. It's really hard to estimate the probabilities. Oftentimes, we will, as we're doing problems, we'll have a hard time identifying if our answer seems right sometimes. But we'll see that as we do more examples, I suppose. When we were determining the total number of ways we could arrange 6 numbers, we basically came up with something known as the factorial rule, where we're trying to figure out the number of ways of arranging n distinct items, where we're going to pick all n of them. When we're doing this, factorial notation just means multiply 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. And we'll even define 0 factorial. 0 factorial will be defined as 1. It's the number of ways of arranging nothing. We'll say it's one way. So we might be able to come up with formulas for our 649 problem involving factorial. When we did the problem, we had 49, 48, 47, 46, 45, 44, all multiplied together. It looks like 49 factorial, but it's not quite because it doesn't keep going. So we need to find a way to express this. How do we get rid of the values we don't want? Well, what we can do is basically work on cancellation here. 49 factorial is 49, 48, 47, 46, 45, 44 times 43 factorial. Maybe I could write that. So if we take our lottery example, if we want to know what 49 down to 44 is, we can just divide 49 factorial, divided by 43 factorial, and we're left with what we want. This is a formula for permutations. This is the number of ways of picking, 6 items from 49 when they're all distinct and the order of them does not matter. When order does matter, then you end up with the larger value. So here we go. Well, sorry, this is when order did matter. Remember when we first started this out, we had 10 billion and we had the value was too high. So that's what this would calculate. It's the number of ways that we could choose 6 items from a group of 49 when the order did matter. We'll call this permutations. So we'll have a little formula here, 49p6. The formula in general is NPR, where N and R are subscripts. N is the size of the group of unique items, and then R is the size of the subset. This is the case. This is what would yield us the 100 or the 10 billion, or in the lottery example. Sometimes items in the group are identical and we can't tell them apart. Then the formula changes a bit, where we divide the formula by the number of ways you can essentially arrange the ones that repeat. We'll see an example of this. I call this second one the Mississippi rule, because the common example is how many ways can you rearrange the letters in the word Mississippi? And there are repeated letters in it, like this one, Mississippi. If we count the total number of letters there, we'll see that there are 11 letters in Mississippi. So if they were all distinct and we were choosing all the letters, there would be 11 factorial different ways of rearranging them. However, if I take the 2 P's in the word and I just swap them, it's the exact same word. Or if I swap 2 I's or 2 S's, it doesn't change it. It's indistinguishable. So we have to basically reduce it by the total number of S's I see. I see 4 S's. So 4 factorial for that. And I see 4 I's. And I see 2 P's. And I see 1 M. So the numbers on the bottom should always add up to whatever's on the top. Now to calculate this thing, we'll just go 11, 10, 9, 8, 7, and keep going. And then the denominator is 4, 3, 2, 1, 4, 3, 2, 1, 2, 1, and 1. And you'll see that the calculation here isn't too bad to do, as a lot of stuff cancels. 4, 3, 2, 1 cancels 4, 3, 2, 1. This 3 and this 2 cancels with this 6. Maybe this 4 and this 2 cancels with the 8. And then I just have to multiply what's left. It's 11 times 10 times 9 times 7 times 5. The thing is, I have no idea what I'm going to write down here. Before we started, if I asked, how many different ways are there of rearranging these letters? I think if you told me it was 1,000,000, I might think it was a little high. If you told me it was 3,000, I might be okay. It's really hard to judge these. It turns out that this is 34,650. Of course, you don't have to expand these out and do all this cancellation. I was just trying to show you that that's one way of dealing with factorial. Our calculators have a factorial button on them somewhere. If you look on your calculator, it's like above the 4 button, there's a red little notation there for n factorial. So if we wanted to solve this problem, we could say 11, then second factorial, and then divide it by, and we need to divide by 4 second factorial times, oops, oh no, let me try that again, 11 second factorial divided by, and put brackets here so that I can hopefully just chain these together, 4 factorial and 4 factorial and 2 factorial and 1 factorial, which is 1. So I'll save myself a couple button pushes, and you'll see that we end up with 34,650. So now you know where your factorial button is on your calculator. Just be aware that you probably never even looked at above some of those buttons on your calculator before. And you don't even need to be in stats mode to use that. That's just there. Some more counting examples to go through here. A byte consists of 8 bits. How many different bytes are there? I think we'll just approach this with the multiplication rule. A byte has 8 spots, and a bit is a 0 or a 1. So each one of these positions can be a 1 or a 0. So I have 2 choices for the first spot, and then I have 2 choices for the next, and 2 more, and 2 more. And I'm saying and, so I'm going to end up with 2 to the power of 8, which is 256 different 8-bit bytes. There we're just using the basic multiplication rule, didn't require any factorial, because each position always had 2 choices. It wasn't decreasing as we filled in the list. Another little example here, it says we have a network and there are 5 nodes in the network. So here are my 5 nodes, and it's asking me to count how many paths are there through this network, assuming that everything is connected to everything. So you can go from node 1 to node 2. And it looks like it's asking us for, suppose we want to get through the entire network. So I want to send information from one node to all the nodes. So I could go 1, 2, then 5, then 3, then to 4. That's one path. Or I could go 1 to 5, to 3, to 4, etc., and so on. We want to count how many paths there are. And it's quite a few, I guess. It sort of also depends on, this question doesn't look very well defined. I don't know if we get to choose our starting point. So if the information could start at any of the spots, that will affect this a little bit. Let's suppose we're starting at 1. It has 4 options. And then after it gets to one of its options, that option will have 3 different places it can go. It says that we can't go back. Yeah, once it is visited, it can't be revisited. So the first, we had 4 options. Then once we got to an option, we only had 3 choices left. Then say we're here, then we just have 2 options. And once we're here, we would only have 1 option. So we initially have, 5 different nodes we could start from. And then after that, there will be 4 left, and then 3, and then 2, and then 1. And that will give us all the possible paths through our network. I guess that's otherwise known as 5 factorial, which is 20 times 6, 120. So there are 120 different ways to get through this network. I don't love this question because it isn't clear as to, are you forced to start at a certain spot? Like if you always have to begin at position 1, well then the answer is 4 times 3 times 2 times 1. So significantly less. So I'll try to be clear if I'm asking you guys questions, or if I'm ever asking you guys questions and you get it wrong because of some sort of ambiguity like that, let me know. Try to be fair about such things. More examples here. We have an array that contains 7 distinct elements. How many subarrays can we make that are of size 3? This is a case where maybe we should write down an array. There's my array of 7 distinct things that I can, distinguish from one another. And then I'm going to take selections of size 3. How many different ways can I do that? Does the order of these really matter? I guess it's, part of the question, is A, B, C, D, E, F, G different than, B, A, C, D, E, F, G? Because that will affect what our answer would be. Or if I take an array that is, I'm going to look at subsets. Right, I have 3 spots to fill. And my first spot, I can put any of these things in. So I certainly have 7 choices. And then I have 6 choices left because I can't pick the same one again. And then I have 5 left. So just using the fundamental counting rule, I think we can arrive at this answer. Let's see, that's 210 different ways. Or we could use our permutation notation. This is that exact example where we have 7 things and we're choosing a subset of size 3. And it seems like the order of these maybe does matter. But again, it's not completely clear in this example if that's what they mean. So let's say that it does matter, so that ABC is different than CBA. If we did the permutation rule, it works out as 7 factorial. It's n factorial, n is 7, divided by n minus r. So 7 minus 3 factorial. So we have 7 factorial over 4 factorial, which will work out to be exactly what we just wrote. 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. And we have cancellation. Get 210 ways. Your calculator actually has this permutation button on it as well. Clear out what we did on the last one. If you look above your button number 6, you'll see an NPR button. Let's see if we can get the syntax to work out. I believe we have to type the 7 first, then shift or second NPR, and then type the 3 and enter. So your calculator is pretty sweet. It does a lot of this, heavy lifting for us. On a test, you're certainly welcome to just write that down as your answer. Right, 7p3 equals 210. I'll assume that you knew how to use your calculator to get there. When we did the 649 example, we had to, sorry, I have to refresh my screen here. We had to divide our 10 billion ways by 720, the number of ways of arranging a group of 6. That turns out to be the combinations rule. It's NCR, where we take the number of permutations and divide it by the number of permutations you can have in each subset. So the notation NCR, sometimes we write it as this, N choosing R. This isn't as a fraction, it's just, N choosing R. You'll see this when you see this notation more commonly in like sequences of series, or I've seen it often like if we represent Pascal's triangle, you'll see the combinations written using this notation. But on your calculator, the button is NCR. It's basically, you don't even really need a button for it. If you already have your NPR, you just take the number of permutations and then divide it by, you have a factorial button, the R factorial. So the formula is just this. Simplifies. Some examples, maybe we can see the difference between permutations and combinations. In fact, that's how I basically have this example in my head, and when I see new problems, I go, how does it apply to some problem that I already know? Math department has 20 instructors. We need to make a committee to hire people. So we get 5 people together to be, the interview committee. How many different committees can we come up with? Now, the first thing we have to ask is, does the order of the people on the selection committee matter? If it's Paul, Scott, Brenda, Andrew, and Sandy, is that the same committee as if we had said it was Sandy, Paul, Scott, Andrew, and Brenda? And I think the answer is they're the same committee, like the order of them doesn't matter. So this is combinations. Paul, I'll write it. I was losing track of it just saying it. Paul, Scott, Andrew, Brenda, and Sandy. Is that the same committee as Sandy, Paul, Scott, Andrew, and Brenda? And I'd say they're the same. And as a result, we can say we have 20 people, and we are choosing a subset of size 5. So it's combinations. This is 20 factorial over 20 minus the 5 factorial. And then what makes this different than permutations is that we also divide by 5 factorial. You have a handy-dandy combinations button on your calculator as well. It's above, let's see if we can find it here. It's above the number 5 in your calculator. So in this case, I have 20 second NCR, and then we're choosing 5, and we hit enter, and it's 15,504. It's a big number. It's, rather surprising how big that is. 15,504 different ways of forming a committee out of 5 people in the math department. I've been at BCIT a long time, and I've managed to stay off of the hiring committee, partially because there are a lot of ways it can occur, and I try to be part of the ones that don't occur. We changed the question slightly. Now we still have 20 instructors in the math department, and we're still choosing 5 people. But now when we pick them, they're going to have offices. One person is the president, another person's the vice president, another one's the secretary, treasurer, and independent observer. Now, because there's no actual order associated with those things necessarily, but it does make each group of 5 maybe different. If Paul is the president, Scott is the vice president, Andrew's the secretary, Brenda's the treasurer, and Sandy's the observer, it's a different committee from Brenda being the president and Sandy being the vice president, Paul being the secretary, etc. So here, by adding those officers, or those name delegations, we've now introduced order. So order matters. So when we do this, it's just 20p5. So there's going to be even more. It'll be 20 factorial over 20 minus 5 factorial, which is 20, 19, 18, 17, 16, 15, down to 1. All over. The bottom is 15 factorial, so 15, 14, down to 1. And you see that there's all that cancellation, so it's not too bad to calculate that. It's just 20 times 19 times 18 times 17 times 16, but it ends up being a pretty big number in a hurry. It's 1.86 million, 480 different hiring committees when the officers are part of the equation. One thing that I find interesting about this is, one, the numbers are bigger than I would imagine, so I have a hard time predicting what I'm going to get. And the other thing I find interesting is my whole life I've maybe used the word combination wrong. When I go to my locker and I try to open the lock, I call it my combination locker. However, the order in which I put the numbers in matters. So technically, I'm opening a permutation lock, not a combination lock. Order matters on those locks. So we've somehow the word combination got into our vernacular in the wrong way. So I try to be more careful now. But only a nerd would probably say I'm going to go and open my permutation lock. But, nerds kind of rule the world, so that's okay. We did the probability of getting a flush back at the beginning of this lecture when we used a little program in order to get the answer. Now that was, I had to do 100. I think what did I do? 100 billion or something. Simulation of 100 billion. But this can be done, analytically. Now that we have a little bit of terminology, when you get 5 cards in your hand, we have to ask ourselves, does the order of them matter? If I get dealt 2, 5, 7, 9, and a jack, is it the same hand if I have a jack 9, 7, 5, 2? And I think the answer is they're the same hand. So that's the first thing we need to start thinking about is does the order matter or not matter? And I think we can say that the order of the cards in the hand don't matter at all, because we can move them around in our hand as much as we want, and it's still the same, type of hand. So counting the number of flushes will take a little bit of strategy. I need to basically think of it like this, where I choose a suit for my flush, and then I choose 5 cards from that suit. So that's the strategy. I need a suit and 5 cards of that suit. So to make a flush, first pick the suit. And there are 4 different suits. And then I need to get 5 cards. Of that suit. And once I've done that, I've found my flush. So once I've picked a suit, there are 13 cards in that suit. So I have 13 cards, and I want to pick 5 of them. This is another notation for combinations. But the problem with this strategy is I've included the straight flushes and the royal flushes, so I better subtract those out. So let's figure those out. In poker, you can have a flush that starts low or high, so they can go 1, 2, 3, 4, 5, 6. That's a flush. And then 2, 3, straight. 4, 5, 6, 7 is a straight, etc., until I get up to 10. 10, jack, queen, king, ace. That's the highest flush, the royal flush. So how many of these are there? I guess my straight could start with an ace, or it could start with a 2 or a 3 or 4 or 5 or 6 or 7, all the way up to 10. So it looks like there are 10 of these. But there's going to be 1 for each suit. Like I could have ace, 2, 3, 4, 5, 6 of hearts, or I could have ace, 2, 3, 4, 5, 6 of diamonds or spades or clubs. So there's going to be 4 of each one of these. So 4 times 10 is 40 straight or royal flushes. So now we just need to do I think that's the logic to it. Now we just need to calculate. So, it's 4 times, maybe I'll write it as, that 13C5 minus 40. Let's try it on our calculator. 4 times, and it's 13 second, choose 5, and then subtract out the 40 that are royal flushes and straight flushes, and we get the magic number of 5,108. So there are 5,108 different flushes. Now to calculate, we're looking for the probability here. So we need to figure out the total number of poker hands. To figure out those, it's even easier. There are 52 cards in the deck, and I need to pick 5 of them. Which is 52 factorial over 52 minus 5 factorial and 5 factorial. We could just do it on our calculator. 52, choosing 5 things. Order of the 5 doesn't matter. We get 2.6 million, 2598960. So the probability then of a flush is just the ratio, 5108 divided by 2.6 million. Which we saw earlier was 0.001965 something. I think the next digit was 4. So counting, it can be a relatively complicated thing, because you do have to always be asking yourself if the order matters or not. That's the key part to whether you have permutations or combinations when you're doing these problems. So now we can move on into I think we've done enough examples there of counting and basic probability. We can actually talk about the main rules of probability, or the axioms. Most of these should be pretty obvious. Impossible events have probabilities of zeros. The probability of an event that must occur or is certain has to be 1. All other probabilities must be between 0 and 1. If you ever get a probability over 100% or over 1, you know you've done something wrong. I hate when people give 110% on their assignment. It just drives me crazy. We're going to take advantage of the fact that the probability has to add up, or has to be between 0 and 1, by looking at the complement. I'll denote complement of event A with a bar over the top, or sometimes with A with a superscript C. That's the complement of A, or the opposite of A. So because of that, the probability of some event A happening plus the probability that A doesn't happen has to always equal 1. They're not 50-50 necessarily, but the sum has to always equal 1. Everything happens or doesn't happen. And we can take advantage of this property to solve more complicated questions, where, say, you want to find the probability of something happening. It's often easier to find the probability that it doesn't. So we'll just do 1 minus the probability of something not happening equals the probability that it does. We're going to use that technique very frequently whenever we have events, compound events that are an OR type situation. There's a little, Venn diagram here that didn't show up that great, where I have the whole universe here having an area of 1, and then the probability of A takes up some area within that, and the complement of it is the area outside. When I take the area outside plus the area of what A was, I get a total that equals 1. The other thing we're supposed to get from this is that oftentimes we view probability as area. So the sooner we start imagining that relationship, the easier our life will be going forward. We're going to use this complement technique when we do the birthday problem later. It's a famous question. The next question, we probably wouldn't necessarily need it so much, but let's give this one a try. We're looking at a sample of 10 transmission housings. Over the long run, we know that 6% of these things are defective. So what is the probability that 0 defective housings are found during our hourly inspection where we looked at 10? Basically, we want no bad ones in our group of 10, or we want all good ones. We could probably just make like a little chart here. Here are my 10 spots. I need a good one, a good one, a good one, a good one. They need to all be good to have 0 defective. So I am sort of using the complement here rather than looking at defectives. I've sort of switched my thinking to, it'd be easier to solve this in terms of, all good. The probability that the first one is good is the complement of this 6%. If there's a 6% chance they're bad, then there's a 94% chance it's good. And I need all 10 of these. And the probability doesn't change. We're manufacturing thousands of these things. So we don't need to decrease, as we're drawing, a few out of the batch. 0.94 raised to the 10th power, I get, there's about a 53.8. I don't care if you answer this as a decimal because it just asks for probability. If you prefer percent, that's fine. Either answer will do. Probability could be expressed either way. Or if you wanted to calculate the fraction for this, I guess you could leave it as a fraction. Another example here where we're looking at more kids, family with kids. What are the chances that if you have 3 kids that exactly 2 of them are boys? Assume that there are our stats book is dated, so there really are only 2 options. So let's assume that they're equally likely. Maybe someday in the future they'll update these things. But because it does show up in the text, I wanted to make sure you're aware or used to seeing such a thing, even though it's not necessarily the modern view of things anymore. We have 3 kids. I could draw a tree diagram. So I don't have any kids, and then I have a boy, or I have a girl. And then after my boy, I might get another boy, or I might get a girl. And then after having 2 boys, I could get a boy or a girl. And this is going to basically help me systematically list all the different permutations of families I could end up with if I have 3 kids. It's a situation where, I guess the order matters. If I have a boy and then 2 girls, that's a different family than if I have 2 girls and then a boy. So like I said with these, that is something to keep in mind all the time. I decided to list them all out here so that I could just bring up the terminology of sample space. It's all the possible things that can happen. If I had 50 kids, this would be a tough thing to list out. But with 3, we can. And if you just follow the branches, the first branch went, B, B, B. So one permutation is boy, 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 then boy, boy, girl, boy, girl, boy, boy, girl, girl. And you can do the rest here, boy, boy, girl, boy, boy. So there turned out to be 8 possible families of 3 kids. How many of them have exactly 2 boys? Well, we can just go through and count. here's one that has 2 boys, here's one that has 2 boys, and here's one that has 2 boys. So the probability of exactly 2 boys in 3 kids is 3 out of the total of 8. If we did have to extend, well, maybe we should do girls first. What are the probability of exactly 2 girls? I hope it's the same, or the world is going to get out of whack in a hurry. Probability exactly 2 girls. I guess I see 2 girls here, here, and here, so good. The chances of 2 boys is the same as the chances of getting 2 girls. We would probably have to come up with something a little more sophisticated to calculate this if we were going to larger scale. Let's see if we can do this. If we have a group of 3 and they're all unique, there are 3 factorial ways of arranging them. But we need 2 of them to be boys and 1 of them to be a girl in the 2 boys case. So the 2 boys in the group, if I swap them around, it's still the same thing. I'd still have, if I have boy, boy, girl, and I swap the first 2 boys around, it's still boy, boy, girl. So I need to account for that by dividing by essentially the 2 boys in the group are, indistinguishable because they make my group 2 boys and 1 girl either way. And then I have 1 girl. That's that Mississippi rule. That's the total number of ways then of having 2 boys out of 3 people. Then divide that by the total number of things you can, end up with. You have 2 choices for your first kid, 2 choices for your next kid, 2 choices for your next kid. So 8, 2 times 2 times 2. So we could solve this, using our other techniques here. The numerator there is 3 times 2 times 1 over 2 times 1 times 1, all over 8. And stuff cancels, and you get 3 out of 8. So if we had, 50 kids, we could have 50 factorial and 2 boys and 48 girls. And then the bottom would be, 2 to the 50th. So the technique generalizes. So that is a good thing to know with these sorts of problems, is if I give you a large number, first just write down the smaller version, figure it out, see how it goes, and it might give you insight to solve a bigger problem. More complicated things, we have the addition rule, where we have the probability of A or B. We have a new symbol here. This is from set theory. This just means or. It's the union symbol, A union with B. It's the probability of A plus the probability of B minus the probability that both things happen. Basically, in a Venn diagram here, I have the whole universe, which is 100%, and then part of it is the probability of A, and then part of it is the probability of B. And you'll see that if I add the area of A and the area of B, that I've added the intersection part twice. So I need to take it away once. So that's why there's this subtraction of the intersection. This is basically or, and this is basically and. Union and intersection. Little example, we're going to draw a card from a deck. What's the probability of getting a card that is either red, that's a red or an eighth? So I use my union symbol. From the formula, it's probability of getting a red card plus the probability of getting an ace minus the probability of getting one that is both red and an ace at the same time. Red cards make up half the deck. There are 26 red ones out of the 52 cards. Aces, there's one for each suit, so there's 4 out of 52 aces. And then we subtract out aces that are also red, so there's an ace of hearts and an ace of diamonds, so 2 out of 52. And we get to our conclusion here, 28 out of 52. You can leave your answer like that. You don't even need to reduce the fraction. In fact, I almost prefer if you don't reduce the fraction, because then I can sort of see where it may have come from. I'm not sure why we force everyone to reduce fractions. I can divide 28 by 52 on my calculator just as fast as I can divide 14 by 26 or 7 divided by 13. So yeah, reducing fractions, I'm not sure why we do that, so why we drill that into everybody. This is a problem you probably could have solved without using the formula. It was just showing you that the formula does work. I think most of us would have just imagined, yeah, there are 26 red cards, and then I'll add the 2 black aces to the mix and get 28 out of 52. But it's nice to see that the formulas do work. Sometimes we have things that are mutually exclusive when there is no intersection, meaning you can't have the 2 events can't happen simultaneously. The Venn diagram here, I don't overlap them at all. There is nothing in common for both. It's nice when that happens because the formula becomes more natural, where you just take the probability of A plus the probability of B and you don't have to subtract anything. Well, you are subtracting something, it's just nothing. You're subtracting 0. So maybe we'll run into an example of that as we go through these. Next problem in our list, example 15. We're marching right along. We're rolling dice now. I still have mine out. Should have turned my camera on so you could see me rolling these 1,000 times. I can make another video for you maybe. Here's me rolling dice 1,000 times. I'm asking a question here. What's the probability of getting a total of 7 or 11 when you roll, basic fair dice, not your crazy, Dungeons and Dragons dice, just regular 6-sided die? One way to do this might be to list out the sample space. What are all the possible ways I can roll dice? So, on one of the die, I have 1, 2, 3, 4, 5, and 6 spots. And then the other one, same thing. I'm looking for totals. So sometimes I roll a 1 and a 1, and I get a total of 2. And sometimes I roll 1 and 2, I get a 3, 1 and 3, 1 and 4, etc. And these are my totals. And I can build the whole chart here. I could roll a 2 with a 1, and that's a 3. It's a nice pattern to write out. It allows us to see the entire sample space. These are all the possible sums when rolling 2 dice. What's the probability that the total is a 7 or 11? If we used our formula, it's the probability of getting a total of 7 plus the probability of getting a total of 11 minus the probability of getting both, a total of 7 and 11 at the same time. You can see this is a case where we have mutual exclusivity. You can't roll a total of 7 and 11 at the same time, so we can just essentially say that this is going to be 0. To get our total of 7, we can just look through our list here. How many different ways are there to get 7s? And the answer is 6. And there's a grid there of 36 possible outcomes. Our other option is to get an 11. There are 2 ways to get that. So 2 out of 36. So our final answer there is then 8 out of 36 different ways of rolling 7 or 11. It's a little bit weird. The order of the dice sort of matters. A 1-2 is different than a 2-1. And if you need to, like my dice are colored, so I have a green one and a red one so that I can see that those events are different. But there is only one way to get 1-1, because it's still 1-1 regardless of which way you order them. So yes, order matters here, but it's more subtle. Each of the totals here is not equally likely here. 7s are way more likely than 2s or 12s, for example. So if you're playing some game where you're betting on the total on dice, 7 is the most likely thing, so it would have a lower payout than maybe rolling something like a 12 or a 2. A term that people sometimes mix up with mutually exclusive is independence. Independence refers to when you're repeating an experiment over and over again. Mutually exclusive deals with things happening at the same time. So independence is a term that we use when we're doing things repeatedly, and events are independent if the outcome of one doesn't affect the outcome of another. The coin flip is the common example of, an independent events where you're flipping a coin over and over again, and each flip is independent of what the previous flips were. Just because you saw somebody flip a coin and get heads 3 times, you can't presume that the next one is more likely to be heads or tail. The coin basically is memoryless in that way. The events are said to be independent. But sometimes when we repeat events over and over, we do have dependence, where as you see one outcome, it might affect what happens next. We'll write that dependence using some fancy notation here. What's the probability of B happening given that A already did? So that's what that bar or pipe means. It just means given. Now that we have that dependence notation, it allows us to come up with the multiplication rule where we're doing something repeatedly. What's the probability of A happening and then B happening? Like, this intersection notation is a little confusing. In the addition rule, it meant simultaneously, and in the multiplication rule, it means sort of in some sort of order, A happening and then B happening. If you have independence, you just take the probability of A times the probability of B. If you have dependence, you find the probability of the first thing happening and then multiply it by the probability that the second thing happens, given that you know the results of the first. So that doesn't mean a division in there, it just means given. The example with the coin flip, what's the probability of getting 2 heads in 2 flips? So I need a head on my first flip, and then I need a head on my second flip. These things are independent, so I can just multiply probability of getting a head on the first times the probability of getting a head on the second, which is just 1/2 for the first, and it's 1/2 for the second. So we get a total of 1/4. This is because they are independent. We need an example of dependence to sort of get this topic, understood, I think. Drawing cards from a deck can be a dependent process, assuming that when you draw a card from a deck, you don't put it back in. So we'll do the example of, what are your chances of getting pocket rockets in Texas Hold'em poker? That's when you get dealt 2 aces to begin with. What are your chances of getting an ace and then another ace from a standard deck of cards? So I need an ace, I'll call it ace 1, and then I need ace number 2. It's the probability of getting the first one times the probability of getting the second one, given that I know that the first one was already an ace. It looks more complicated than it actually is. To get your first ace, there are 4 aces in the deck and 52 cards. So you have to have that occur. And then next, you need to get another ace. But when you go to draw your next card, there aren't 4 left in the deck anymore. There are only 3. And there aren't 52 cards in the deck anymore. There are only 51 remaining. So the second event depends on what happened on the first one. It's harder to get that second ace because you've removed one already. This probability ends up being, just the product there, which is relatively low. It's 0.0045248886. So roughly, 4.5 times in, what is that, 10,000? Yeah, like 4.5 times in every 10,000 hands, or say roughly, if you're lucky, 5 times per 1,000 hands, you'd sort of expect to get this hand. So when you get this hand, you're pretty excited. It's supposed to be the best hand in Texas Hold'em poker because it's relatively rare. So you have to be careful not to get too excited and let people know that that's what you have. Of course, the funny thing about this is the probability of basically getting any 2 specific cards. This is or any pair. This is probability of getting, 2 6s or 2 9s or 2 jacks. They all have the same probability, but aces are better in poker because they're higher than the other cards, it doesn't make them more rare than a pair of jacks, but because they're better, they're bigger, so they're considered better. I think we've done a lot today. Let's end the video here, and we'll take this up in another video. Hope you guys all have a great day. See you next time.